All right, here we're going to do another little miscellaneous lesson, which is going to be over how do I take the derivative of an inverse function. Kind of a little bit strange, but it's not going to be, I don't think, super terribly impossible, although it is a little bit weird. Okay, let's do a little bit of pre-cal review. What is an inverse function? Well, a function g is the inverse of f if and only if when you do the two composites. So when you do f of g, that's your fog, right? So f of g of x. If you do f of g and you do g of f, when you do both of those composites, so if you plug in f into g and if you plug g into f, both of the composites have to end up giving you just a regular singular linear x. If you do both of those composites, that's algebraically how you can confirm that two things are inverses of each other. Graphically, we know that an inverse and its function, or the function and its inverse, they're going to be reflections over the line y equals x. Right? And an example of those would be like your natural log graph, like y equals ln of x, and then its inverse, which is the exponential function, which is like this, right? Y equals e to the x. Those are inverses, and they're both the reflections over that line, y equals x. The inverse, you denote it with that f to the negative first power. Kind of one exception would be for your inverse trig, right? Arc sine of x, you could see it written as arc sine or either as sine inverse. Right, the negative one notation gets a little bit confusing with do you mean reciprocal or do you mean inverse? But the context of the question should generally make it fairly obvious which one you want. Properties of inverses. If g is the inverse of f, then f is the inverse of g. They always come in groups of twos. The domain of the inverse is the range of the original, right? Domain of the inverse is the range of the original, and the range of the inverse, that's the domain of the original, right? So the x's and the y's swap, right? That's how we find an inverse. You go and you change the x's and the y's, and you solve it for y. The whole idea with an inverse is that it's a reflection over the line y equals x, so the x's and the y's are going to swap. So when I have my original function and the domain and the range, and then you have the inverse with the domain and the range, these two things should match, and then those two things should match. Of course, those are going to be x values, those are going to be y values, those are going to be x, those are going to be y's. But like the numbers that defines the x's and define the y's for the range, those sets would be the same. Okay, so the x's and the y's swap places. And then not every function has an inverse. We call those non-invertible. But if it does have an inverse, it only has one, right? Inverses are unique. One function cannot have multiple inverses. Some functions don't even have an inverse. Some do, but if they do, they only have the one. All right, let's go through and let's do this last little bit of algebra, and then we'll get into the calculus. Here we go. Given this function where we have f equals the square root of x minus 1, it says, let's go ahead and find what the inverse of that function is. Okay, so algebraically, how do we go through and find an inverse? Well, what we're going to do, I'll do part A down here. Sure, I'm going to do it in red. For the part A, what we do is we just switch the x's and the y's, right? Here's my original. Y equals the square root of x minus 1. So I'm going to swap the x's and the y's. So x equals the square root y minus 1, and now I'm going to solve it for y. So I would square both sides, then I would add the 1 over. Oh, I need the plus 1, don't I? Plus 1 equals y. And so that would be my inverse. Right, now we're just going to change it. Instead of y, we'll change it to the inverse. It's going to be x squared plus 1. Okay, so there would be how you find, algebraically, what the inverse function is. Right? You swap the x's and the y's, then you solve it for the new y. And then part B, we're going to graph them on the same set of axes. All right, so let's go ahead and let's get a decent graph. We'll do part B over here. I don't know why I got 2 extra lines because I hit it with my fingernail. Here's part B. Let's go ahead and graph it. So I'm going to graph the original. How about in green? So it's your square root function, shifted 1 to the right. So there's 1 it would look something more like that. I'm going to call that one f. And then the original, or sorry, that is the original, the inverse. Now, the inverse full function, right, it's this parabola, x squared plus 1. So it's going to be shifted up 1, and there would be the right side of the parabola, and then here would be the left side. But we have to think to ourselves, do I really want that full parabola, right, for the inverse? Do I really want that full x squared plus 1 parabola? And the answer to that question is no. We don't really want that left side, right? If we have it there, that's cool. But if we really wanted the left side of the parabola, we would have had the bottom side of the horizontal one. But since the original function was only the positive part of the horizontal parabola, that means my inverse should only be the positive part, the right of the vertical parabola. If we had had that, then we would have this, but we didn't. So we don't, right? There was a range restriction on that original. That original was only existing from 0 and upwards. So that means there is a domain restriction on this inverse. It should only exist for everything to the right of 0. Right? I don't want the full parabola. I only want the right side of it because I didn't have the full horizontal parabola. I only had the top part of it. Okay, so there we go. We got the inverse graph done, and we also have the original done. So everything on part B is now done. Right? We got A, got it. We did B, very good. Describe the relationships between the graphs. Right? Well, this is true for everything, right? For all inverses, they are. Let's just do part C. They are reflections over the line y equals x. Right? Sorry, it's a little sloppy. I don't really care. That's always the relationship between any two inverses, right, and their graphs. They're the reflections over the line y equals x. And then let's do this last thing. Let's do the domain and the range for the original function and for the inverse. Right, let's just do, here we go, part D. Let's just do the original first. Right, the domain for the original, it starts at 1, and then it goes from 1 all the way to the right. So the domain for the original is going to be 1 to infinity. Now that's x equals 1 to infinity, or x is greater than or equal to 1, right? You could write it like this, or you could write it x greater than or equal to 1, or you could write 1 x to infinity. Like there's a couple ways to write it. I'm just going to use kind of the interval notation with the bracket on the 1 because it's inclusive, parenthesis on the infinity. And then the range would be from 0 up to infinity. And then how do we get the domain and the range of the inverse? Well, there's two ways. You could just copy. Like I know whatever the domain of the original is, the range of the inverse should match it. And let's check. Does that graph exist from 1 upwards? Yep, there's 1, and then upwards. Yep, that looks good. What about the domain of the inverse? Well, the range of the original, 0 to infinity, that should be the domain of the inverse. And yes, since this range was 0 and then eventually hits all those y values, that means the domain should be 0 and then everything to the right. So you can either look at the graph of the inverse, or you could just simply take those two things and then switch them. And then remember that that's x's, that's y's, this is x's, that's y's. So if you wrote it slightly differently, right, don't say stuff about y's for a domain, don't say stuff about x's for a range, but if you write it with the kind of the interval notation, there's no x's and no y's. That's why it's, I think, a little bit easier. But there we have it. That's a pretty good review from our pre-cal of inverse functions. Now let's get into the calculus stuff. And this is going to be a little bit weird. The formula that we're going to see on the next page is a little bit weird, but actually doing these questions is pretty easy, right? But what we have to understand is that there's really like two different parallel tracks, right? There's going to be the original function. We'll say, hey, over here is the original function, and then we'll go over here. This will end up being the inverse. So we have these two parallel tracks, one of them with the original function, and then the other with the inverse, right? And what we're going to need to be paying attention to is that Like the original function is going to be using one specific x value. And for us in this example, that x value for the original is 2. And then there's going to be a different x value over here for the inverse. And we can see that that x value for the inverse is 8. So there's the two parallel tracks, the original function with its x value, and then the inverse function which it's with x, which is a different x value over on the other side. But there's the two parallel tracks, original with its value, the inverse with a different x value. Okay, but is there a relationship between those two x values? Yes, let's look at it. Here we go. My original function is x cubed. If I were to take 2 and plug it in, 2 cubed, that would be 8. So if I plugged in 2 into the original, I get out 8. And let's go back and look at this inverse side. Like, hey, my inverse function is the cube root. And what was the x value for the inverse? Well, it was the y value from the x value of the original, right? The 2 and the 8 are related. If I plug in 2 into the original, I should get out 8. And that 8 is the corresponding value that you would use for the inverse, right? So here we go. F inverse of 8. If I were to plug in 8 into this, the cube root of 8, that's 2. So I have the original function with its x value, and then I have the inverse with its x value. Now those values are related. If I plug in 1, I should get out the other. If I plug in 2 to the original, I get out 8, which is the value for the inverse. Or if I plug in 8 into the inverse function, I should get out 2, which is the value you would use for the original. Right? So there's these two parallel tracks. The original with its value, which in this case is 2, and then there's the inverse with a different value, which in this case is 8. And then those two tracks are going to be running kind of parallel to each other. Now we can take the derivatives of both of these. Let's do the original side first, and then we'll do the inverse. The derivative of x cubed is easy. It's 3x squared. And then I can plug in my x value to that side. 3, 2 squared. That's going to end up giving me 12. Right, so the derivative of the original at 2 is 12. But really what we want today is we want to end up finding what's the derivative of the inverse with the inverse's value, right? What's the derivative of that inverse function? So let's go for it. Here we had x to the 1/3 power, right? That's your cube root. So if I were to take the derivative, we would end up getting 1/3 x to the negative 2/3, aka 1 over 3 x to the 2/3, right? So since I had the inverse function, and it was a pretty easy one, I could take the derivative, and then since I have this equation for the derivative of the inverse, I could just plug in 8 into it. Right, here we go, 8 to the 2/3 power. You can either do 8 squared, which is 64, and then cube root it, which is 4, or you could do the cube root of 8, which is 2, and you could do 2 squared, which is 4. Either way, you're going to get that 8 to the 2/3 power is 4, and then we're going to end up finding that the derivative of the inverse with 8 is going to be 1/12. Okay, so I had the derivative of the original with 2, that was 12, and then I have the derivative of the inverse at 8, that's 1/12. And then what is the relationship between these two things, between the 12 and the 1/12? Please don't say inverses, okay? They're not inverses, they are reciprocals. Okay, and that's always going to be the relationship with our calculus between an original function and its inverse and the two derivatives. Now, our goal is pretty much always to get to that bottom right. The goal is pretty much always to get to the derivative of the inverse. Sometimes you will have the inverse function. And if you have the inverse function, you can take the derivative of it. And if you have the derivative of the inverse, you can just plug in your value into it, and that's straight away, right? Pretty easy. But a lot of the times we won't have the equation of that inverse. And if I don't have the inverse, I can't take the derivative of it. And if I don't have the derivative, I can't plug in. Right? So if I really don't know a lot about that inverse side, I may not necessarily be able to work on this right side of my two little parallel tracks. So if I don't have the inverse, what I'm going to have to do is switch it over. And I'm going to be able to work and do everything with the original function. But if I switch it over and if I do all this work for the original, I'm going to have to switch it back to get to that answer for the derivative of the inverse. How we switch it back at the end is just taking the reciprocal. This process is a little bit weird, and the formula that we're about to see at the top of the next page, it's ugly. But I would just encourage you to remember the process and then the formula. It's the same thing, right? The formula and the process, they're the same. But the process is just easier, I think, to remember. All right, here we go. Let me move it over to the next page, and then we'll fly through these notes, and then we'll be done. All righty, here we go. I think that's probably good enough. We've got let f be a function so that it is differentiable on the interval I. If f has an inverse function, g, then g is differentiable at any point for which f prime of g of x is not 0, right? We don't want to divide by 0, that's bad. And it gives us g prime is 1 over f prime of g. Okay, so whatever. Let's look at this formula, right? If I want to take the derivative of the inverse, here's what it is. 1 over f prime f inverse of a. Ooh, that's such a nasty formula, right? It's just not super pretty. It's a little bit confusing. There's primes, there's inverses, there's parentheses. There's just a whole lot going on. That's a kind of ugly formula to try to remember. But generally, the process is 3 steps. Right? I'm going to break them down for you. The first step would be to do this. And that's really, right, if I can't work with the inverse, the first step is to find the correct x value, not for the inverse side, but for the original function. Right? There's the 2 parallel tracks. You have the original function with its value, and then you have the inverse with a different value. We're pretty much always going to know the inverse and its value. And so the first thing is, hey, I'm going to figure out what's that corresponding number for the original function. And that's all f inverse of a is. That's switching it over and finding what's the correct x value for that original function. But then the second step would be you were going to take the derivative of that number. Okay, so you would take f prime and you would evaluate it with that number from part 1, right? So you find the correct x value for the original function. And then we're going to take the derivative of the original function, and then we're going to evaluate it at that new number. Not with the number we started with. That's the inverse's value. But we're going to use the new number, which corresponds to my original function. Right? And then the third step, which corresponds to the 1 over, that third step is just going to be to reciprocate, right? Reciprocal. I can't spell. I think I got it. Yeah. We're going to take the reciprocal. That's all the 3 steps are, right? The formula is kind of ugly. The formula says the same thing as the process. But the first thing, which is green, is to do f inverse of a. That's, hey, if I'm given the inverse, if I'm given the x value for the inverse, I really want to find the x value for the original function. And that's what f inverse of a is. Like on the previous example, we had f inverse of 8, and that gave us 2, right? 2 was the value for the original, just like how 8 was the value for the inverse. So I want to find what's that value for the original. But then I'm going to do all the calculus. I'm going to do f prime of that new number. I'm going to take the calculus with the original function, and then I'm going to plug in the value for the original function. And then I don't want the value from the derivative of the original. I want to somehow connect it back to the value of the inverse. And so I'm just going to take the reciprocal. The 1 over part in the formula just means do the reciprocal. So the formula is kind of ugly. I think it's easier to just remember the process. Right? Let's go through it. A couple of examples here for us. All right, first one, it says f of 3 is 5. Then it says f prime of 3 is 7/2. And it says find f inverse prime of 5. Okay, let's think about it, right? We've got the 2 sides. I don't remember what sides I did. I think I did the original with red, and I think I did the inverse with blue. I don't really remember. But let's think about it. Okay, what x value does it want us, right? It wants us to eventually get to f inverse prime, And then what number is it wanting us to use for the inverse side? It wants us to use 5. Okay, so the first step, which is your f inverse of a, your first step is like, hey, I really don't know anything about the inverse function. So it's not going to be possible for me to get to this, right? Because if I don't have the inverse, I can't take the derivative. And if I don't have the derivative, I can't plug in 5. So I really can't do everything on that right side. So instead, I'm going to have to switch it over. And I'm going to come over to the original function, and I'm going to work with that side because I know stuff about the original function. But the first step is this find the x value for the original, right? It's the f inverse of a. I'm going to find what's this correct x value for the original function's side of these parallel tracks. It's not 5. 5 is the value for the inverse. We have to figure out what the correct value for the original is. So we're doing f inverse of 5, right? It's like this part of the formula, f inverse of 5. And we're basically trying to figure out f of what gives me out 5. Just like how the 2 and the 8 were related in that previous example, the 5 and this mystery number, they're related in this example. And the question tells us, catch it, 3. Right? And you can also just tell 3 is the number that we're using consistently for the original function. We had f of 3 was 5, and then I had f prime of 3. So 3 is the value for the original. 5 is the value for the inverse. But then 3 is the value for that original. All right, so the first thing would be find that x value for the original, which we just did. It's 3. Right? And that's kind of obvious because it's right there for you. Right? Now, if I had f, I could take the derivative, and then I would want to take f prime with this new number, 3. But it tells me that, right? It tells me that it's 7/2. So I know the derivative of the original function. But I really want to switch it back, and I want to get to the derivative of the inverse. Now, the original is using 3, the inverse is using 5, that's fine. What's the relationship between the derivative of the original and then the derivative of the inverse, right? They were reciprocals. So if the derivative of the original is 7/2, then the derivative of the inverse is going to end up being 2/7. And that's it, right? This answer is 2/7. It's really a much weirder, kind of seemingly more complicated question than it really ends up being mathematically. What's weird conceptually is that we weren't able to do all the stuff on the right side. So instead, I switched it over, and I did all the stuff with the original function on that side, which meant I need to use a different value. Right? I didn't use 5 with the original. I used 3, because 3 was the value for the original, which corresponded to the 5 for the inverse. But the first thing I had to do was find the value for the original, which was 3. It's obvious in the question, but it was 3. But then I would take and evaluate that derivative, which it gave me, the 7/2. And then I take the reciprocal, therefore 2/7. It's easier to remember the process than it is to remember the formula. Okay, let's move on to the next one. No, not that. No, not that. No, not that. I do that like every video probably. It's probably super annoying. Oh well. Live with it. Here we go. Sometimes we're not going to be given everything. So let's see what we can do with this one. We have f of x, which is x cubed plus 2x minus 1. And it says find f inverse prime of 2. Again, let's try to think about these two different parallel tracks. We have the original function with its value, and then we're going to have the inverse function. And look, what's the inverse function's value? It tells me it's 2. And eventually, I want to get to, hey, there's my inverse. What's the derivative of it at 2, right? I want to know what that answer is going to be. I could potentially try to just brute force it, right? I could try. I'm given the original. If I tried to, let's see, switch the x's and the y's. If I switch the x's and the y's, I could try to do the algebra to get this to y equals, which would mean, hey, there's my original, or there's my inverse function. But that's not something that's going to be very easy or really possible for us to solve it for y, because I've got a y cubed and I've got that plus 2y. that wouldn't be very possible for us to solve for y. And if I can't solve for y, that means I can't get the inverse. And if I don't have the inverse, I can't take the derivative of it. And if I can't take the derivative, I can't plug in 2. So I really am not going to be able to work on that side because I'm not able to find what that inverse function is. Right? So for this one, we don't have any choice. We cannot work on that inverse side. So I'm going to have to switch it over. Right? I'm going to have to do my little witchcraft. I'm going to have to move over here. I'm going to have to work on the original, and then I'll just have to switch it back at the end. And the first step is always finding what this correct value for the original is. Right? That's the f inverse of a part. We know the value for the inverse is 2. So I'm trying to figure out f of what is going to give me out 2. And then that question mark, right, the value that if you plug into the original gives you out 2, which is the value for the inverse, what that question mark is going to be my new x value for this track on the left, for the original function side. Now here, if you have a calculator, right, you could just graph this, or you could set the two things equal to each other, right? Now, you could try to solve it, but again, since it's cubic, we're really not able to solve that by hand. If you had a calculator, you could graph it, find the intersection, or get it all equal to 0, graph it, find the x-intercept. But really for us, we were going to assume that we don't have a calculator. And so how could I potentially solve that without a calculator? Well, we could just try to guess and check, right? Let's just try. Like, what if my question mark is 0? I always try easy guesses first. Let's see, f of 0 would be 0 plus 0 minus 1. All right, so that would be negative 1. Okay, so that didn't work. 0 is not the question mark. Let's try 1. Right? I always like to try easy numbers first. If I tried f of 1, 1 cubed is 1, plus 2 times 1 would be 2, minus 1, 1 minus 1. Ooh, so if I plugged in 1, what do we get out? 2. So is that what we wanted? Yes, right? F of 1 equals 2. So what is my question mark value? What is that new x value going to be for my original function side? Well, it's going to be 1. We couldn't really, sorry, I feel like I'm about to sneeze, and I don't really want to sneeze all over this nice smartboard. We couldn't really solve it by hand, right? We couldn't really set the function equal and solve it by hand because it was cubic. If I had a calculator, it would be super easy. But really guessing and checking, right? Check 0, check 1, check negative 1, check 2. I've really never seen anything that if it's guess and check, it ended up being something besides like 2 or easier. Or it should always be something probably pretty easy for you to get. Right? But guess and check, we ended up finding that here, my x value for my original side is 1. That's the first step. That's your f inverse of a part of the formula. That's your first step in the process, is switching it over to this original side and figuring out what is this new value for the original side. It is not 2. This number is the value for that inverse side. But I need to figure out what's the corresponding value for the original. Right? A little bit of work, but not super difficult. But now I'm going to take the derivative of that original, which is easy. Right? I have the original, no big deal. 3x squared plus 2. And then I could take that derivative, and I'm going to plug it in with 1, not with 2. Remember, 2 is the inverse value. I need to use 1, which is the original value. So that's going to be 3, 1 plus 2. So the derivative of the original gives me out 5. 5 is not the answer. Remember, somehow I need to switch it back and get from the value of the derivative of the original over to the value of the derivative of the inverse. And what's going to be that relationship between the f prime value and then the f inverse prime value? They are reciprocals. So my answer to this question is 1/5. It would not have been possible for us to do all this work because I never knew what that inverse function was. If I knew the inverse function, I could take the derivative. And if I had this derivative, I could just plug in 2. I could kind of just brute force it. But since I couldn't, I had to switch it over to the original side and then work on that side. So I had to find the correct x value, first step. Then I would take and evaluate the derivative of the original with that new value. And then I would just switch it back over to the right side of these parallel tracks by taking the reciprocal. It's a weird little process, but remembering the process, I think, is easier than trying to remember the formula, where there's primes and parentheses just all over the place. It's a little bit weird. All right, I think we got just like two more examples and then we're done. Okay, here we go. Let me just try to, I'm tired of moving this thing, so let me actually just try to get it all out once. Here we go. All right, I'm just setting this up for a minute so I don't have to do as much. F inverse x equals F inverse x equals. So we've got the two parallel tracks. Wonderful. All right, let's look at this example. Here it says G is, okay, instead of F, all right, hold on. I'm sorry, it was G. Okay, I'm just going to change it to F, right? If you don't like G, change it to F. It doesn't matter. But I had the original and I have the inverse. Whether it's F's and G's, it doesn't matter. All right, just change them to F's if you don't like G's. I have the original function, which is the square root of x plus 1. Then I have the inverse. Now, I don't know what the inverse function is, but I know the x value for that inverse. You can see it. The x value for the inverse is 2. Could I potentially find what the inverse function is? Yes, I'm going to in a little bit. But let's kind of use the process first. The first step, remember, is to switch it over, and it's to find, hey, what's this question mark? Like, what is the value so that if I do f of question mark, f of that number, I get out 2. I need to figure out what is that number for the original function side of these parallel tracks. Right, so what could I plug in that gives me out 2? AKA, if I take my function and then I need it to give me out 2, you could either solve it for x, or if you wanted to, you could have the question marks. Either way, you're going to take that function and set it equal to 2. And unlike the previous example, which was cubic and couldn't solve, this one is easy to solve. You could also probably just eyeball test it. You're like, okay, 3 plus 1 would be 4, square root of 4 is 2. Okay, so that question mark, the value that I'm using on this left side of my parallel tracks, value for my original function, it's going to be 3. But that's your first step. It's always to switch it over to the original function and figure out what's the x value that you're using for the original function. Then I can take the derivative of the original function, which is 1 over 2 roots of stuff. Don't need to do chain rule because the derivative of that inside stuff is 1. And then I could evaluate this derivative with the new number, right, the value for the original. So I'm going to have 1 over 3 plus 1 is 4. Let's see, the square root of 4 is 2. 2 times 2 is 4. So the derivative of the original is going to end up giving me 1/4. Okay, so we did all this work, right? We did all this work on the original function side with the original function's x value. But really what I want is to switch it back, because what I wanted at the end was not the derivative of the original. I wanted to find the derivative of the inverse at 2. Okay, but what's the relationship between the derivative of the original and the derivative of the inverse? They're reciprocals. So here this answer is going to be 4. Okay, would I have been able to just brute force this one? Yes. Right, here's how we could have done it. Remember, my original function was square root of x plus 1. I could have solved for the inverse. That's not too bad. X squared minus 1 is going to be y. So there's your inverse function, x squared minus 1. And if you have the inverse function, could I take the derivative of it? Yes, it would be 2x. And if I have that derivative of the inverse, could I just plug in my number to it? Yes. And what's 2 times 2? 4. So that one you could have brute forced and just gotten straight to the answer, because that is a function that we could have found the inverse for. But sometimes you'll have a function that you can't find the inverse for, like the previous example. Or sometimes you really won't even know what the function is, like the first example where we just have the 2 pieces of information. Sometimes it will not be possible for you to do this work on the right. So instead, we switch it over. Remember, we have to find the x value, then we can do all the work over there for the original functions, and then we can just switch it back. How we switch it back is we just take the reciprocal. Right? But sometimes, if you can find the inverse, you could just brute force it. But a lot of the times, that's not going to be possible. Right? But that process, finding the x value for the original, doing all the work for the original, and then taking the reciprocal to switch it back, it'll get you the same answer. Last one. Here we go. Not that. I want that. The x value for the inverse, it tells me, is root 3 over 2. So I need to figure out what the original x function's value is, or the original function's value is. So I'm thinking f of what is going to end up giving me out root 3 over 2, right? So cosine of what is root 3 over 2. And here we go. We should know this, right? From our trigonometry, we know there's 2 points on the unit circle, but it gives me the domain restriction, right? So it wants this one, pi over 6. So the first step is figuring out what is this value for the original functions, right? That's your f inverse of a. F inverse of a here would end up giving us pi over 6. That's the value for the original function. And then I could take and I could evaluate the derivative of that original function. The derivative of cosine is negative sine. And then I could do, okay, the derivative, if I were to plug in pi over 6, would be negative sine of pi over 6. So negative, let's see, what's the sine of pi over 6? Well, if the cosine's root 3 over 2, it doesn't take too much brain power to realize that the sine is the 1/2. So here's the value for the derivative of the original, right? It's negative 1/2. So I'm pretty much done. What's the value? If I have the derivative of the inverse, it's at a different number. That's okay, it's supposed to be. What's the derivative of the inverse going to be? Negative 2, right? Could I have switched it over and found what the inverse function is? Yes, it's literally inverse cosine. Could I take the derivative of it? Yes, right? You should know what that is after having done the transcendental unit. Could I then take that inverse function and then could I, sorry, that was the inverse, see that was the inverse, and that was the inverse's derivative. See, there's primes and apostrophes all over the place. Could I then take that and then plug in my number, which was root 3 over 2? Yes, you could have done negative 1 over the square root, get out of there, and then you could have 1 minus root 3 over 2 squared, and this will eventually still get you to that same answer. It's just harder, right? So that one, we could have found the inverse. We could have done all the work, right? I could have just brute forced it and done all that stuff. But sometimes it's just easier, right? Instead of doing this, you flip it over. So you just find the x value for that side. You do all the work on that side. It's usually easier to work with the original than the inverse. We get the value for the derivative of the original, and then I just switch it back by taking the reciprocal. Right? So it's kind of a weird little process. But generally the formula, let me switch it back up here, right? That formula is kind of ugly. But again, it's really just 3 steps. This thing right here, doing f inverse of a, right? That's really figuring out, okay, f of what equals a, right? That's figuring out what is that new x value for the original. So find the x value, or question mark, for your original function. That's the first step, right? That's the first step. That's the first thing we would do because of our order of operations. That's the first step. The second thing is then to do f prime of that number, right? So second step would be take f prime and evaluate it with x equals number, right? Whatever that value is you just found from doing this first step, you would take and you would evaluate the derivative with that new number. I definitely had the colors backwards, that's okay. And then the third one, right? You do the 1 over part of the formula, and you would just take the reciprocal. And can't spell. Oh well, close enough. Reciprocal. So the process, I think, is easier than the formula. The formula is a little bit of a nightmare. There's primes, there's apostrophes all over the place. There's negative ones, there's parentheses, just really all over the place. So it's kind of a little bit of an unsightly formula. Recipro, it was bothering me. Procal. Right? But if you remember the process, right? There's the 2 parallel tracks. There's like the left side, which is the original function and its x value, and then there's the right side, which is the inverse and its different x value. Right? There's the 2 tracks with the 2 different values. Could those values be the same? Yes, but that would be coincidental, and they're not going to do that on the AP exam because they don't want you to have a coincidence and end up stumbling to the right answer, even though you did the process wrong. Values are going to be different. Could they be the same? Hypothetically, yes. Will they be the same? No. Okay, so there's the 2 different sides, the original with its value, the inverse with its different value. If you can do all the work on the inverse side, great, you can. However, a lot of the times that won't be possible. So you have to switch it over to the original function, find the correct value for that original function, do all the work on that left side, take and evaluate the derivative, but then switch it back by taking the reciprocal. It's kind of a weird little process, but mathematically nothing super hard. It's just weird remembering what to do. Yeah, the formula is a little bit ugly. The process, I think it's easier to just remember the process than the formula. But there you have it. That is how you can take the derivative of an inverse function. Right now, I'm not going to do. There's one more page in the notes, and that has to deal with even and odd functions. If you don't remember what even and odd functions are, well, you probably need to review it a little bit. It's not a huge part, but technically it is part of a pre-calc curriculum, so you really should know it. Even functions, symmetry about the y-axis, therefore f of negative x equals f of x. And then odd functions, right? F of negative x equals negative f of x. Odd functions are symmetry about the origin. Right? You should remember some stuff about even and odd functions. You would have done it right at the beginning of pre-cal. If you're curious, you can go look, right, on my website. You can go look at the notes key. Or if you need to, you can just ask me about this in class. I don't want to do it right now because this video is already long and I'm tired. I don't want to do it. But a little bit of pre-cal review sometimes may be necessary because students typically forget what it means to be an odd or an even function. Numbers can be even and odd. Functions can be even and odd, although most functions end up being neither. But go through, and if you need to, review this on your own. Ask me questions if you need, but I'm not going to go through it in this video because